Hello, this is Meteorology 113, Lecture 6, Air Pollution Emissions. This is the third lecture of Course Module 2, Outdoor Air Pollution. The outline of this lecture is as follows. We will first cover the basic concepts of air pollution emissions. We will distinguish between the emissions from pollution sources, the air concentrations resulting from these emissions as they blow downwind and are subjected to various atmospheric processes along the way, and the health impacts or regulatory consequences based on these resulting concentration levels. We will then cover some basic source classifications and processes of air pollution emissions. Air pollution emissions, basic concepts. Air pollution emissions are the amount of air pollutant coming from a pollution source over some time. That is, it is the rate at which pollution comes from a source. The key points of this are that emissions come from specific sources, for example, the smokestack of a factory or the tailpipe of an automobile. As a rate, emissions are expressed as an amount of air pollution per time, for example, tons per year of SO2 from a smokestack, or the pounds per day of NOx from a tailpipe. Sometimes emissions will be expressed as an amount per area per time. For example, milligrams of hydrocarbon vapors per square kilometer per day. In this example, if we are referring to gas stations across a city, the emissions quantify the milligrams of hydrocarbon vapors due to all filling stations over a square kilometer per day. Emissions expressed in this manner, per area, generally represent the rate of estimated emissions aggregated over all sources over the area. The meaning of a given emission number is often detailed, so one needs to pay special attention when interpreting an emission number, reviewing any definitions, footnotes, or other fine print provided. Air pollution concentrations instead represent the amount of pollutant per overall amount of air. There are two main ways air pollution concentrations are typically expressed. The first, as we have presented throughout preceding lectures, is parts per million or parts per billion. This is the number of molecules per million or billion, if ppb, molecules of air. For example, 40 parts per billion of ozone indicates that there are 40 molecules of ozone per billion molecules of air. Expressing air pollution as ppm or ppb is applicable only for gaseous air pollutants. The other main way concentration is expressed is as mass concentration. This is the mass of pollutant compound per volume of air. For example, 150 micrograms per cubic meter of airborne dust indicates that there are 150 micrograms of dust within a cubic meter of air at the location in question. Whereas ppm or ppb are applicable only for gases, expressing air pollution as mass per unit volume, for example micrograms per cubic meter, is applicable both for gaseous and particulate air pollution. This slide attempts to make more clear the distinction between emissions and concentrations. As well, other related points can be made. The slide shows an example of air pollution emitted from a smokestack. The smokestack is indicated on the left part of the diagram. Emissions from the stack are indicated by the arrow emanating from the depicted stack. This highlights that emissions are always from some source. In this case, we may imagine the arrow coming from the stack, representing a certain rate that pollution is coming from the stack. For example, a certain amount of pounds of SO2 gas per day. Once emitted, the pollution then moves with the wind and disperses and can be subject to various atmospheric processes. This results in certain concentration levels of the pollutant depending on the time and location of downwind travel. In air pollution jargon, the location where pollution is measured or is otherwise of interest are called receptors. This image indicates 3 receptors. The concentration of pollutant is generally different across receptors and depends on the specifics of how the pollution was emitted and the processes these emissions were subjected to as they traveled downwind. The rest of the graphic illustrates the collection of processes that affect pollution once emitted, and therefore determine the precise concentration at various receptors. These processes include transport from the wind, dispersion in the air due to turbulent gusts, eddies, updrafts, and downdrafts, chemical reactions that react the pollutant emitted into other species, absorption of pollutant into cloud water and later washout by precipitation, and further downwind transport to far locations from the wind. Because these processes are all occurring simultaneously, and some more important than others for particular situations, the concentrations resulting from a given emission can depend strongly on meteorological conditions and other factors. Professionals in the field develop expertise and sophisticated methods of taking these into account when understanding and regulating air pollution. In addressing air pollution problems, for example, taking steps for an air district to come into compliance with regulations, or better understanding sources causing pollution exposure, air pollution professionals generally keep in mind these 3 steps as a sequential process. First, emissions come from the source. Second, concentrations are determined as a result of these emissions. And third, the health and regulatory impacts of these concentrations are assessed. This graphic aims to emphasize this forward-in-time approach. The air pollution profession is generally divided into categories of individuals, sub-agencies, or branches that have expertise in either of these 3 divisions. Air pollution emissions, sources, and processes. Emission sources are commonly divided into 2 classes, stationary and mobile. As the name implies, stationary sources are those that are fixed in space. The graphic on the left illustrates a large stationary source, an industrial factory. Within this source, there are several individual sources, or emission units. The emission units comprise each point within the facility where air pollution is emitted. The individual smokestacks within the factory are examples of emission units. Mobile sources are those moving in space, which generally refer to traffic-related sources such as cars, trucks, trains, buses, etc. The graphic on the right shows this. We now cover some individual emission processes, which are classifications for ways by which air pollution is formed and released at the source. A listing of those we will cover in this lecture are seen below, and there are several others that we will not have time to cover. Combustion is the most important common way air pollution is formed anthropogenically, and therefore we will cover this in more depth. The others we will cover more briefly. We first cover combustion. This is the technical term for burning something. In most instances, this specifically means burning a hydrocarbon substance. The substance are used for fuel for some process. The images show common combustion air pollution sources, major factories, mobile sources, and others. Major factories fire their equipment with a large variety of hydrocarbon fuel sources: coal, petroleum-based liquid fuels such as diesel fuel, coke, and others that are derivatives of crude oil. Mobile sources combust gasoline or diesel in internal combustion engines. We provide further details on this slide. A listing of common hydrocarbon fuels are shown in the first bullet. These include gasoline and diesel motor vehicle fuels, jet fuel for planes, coal for power plants, natural gas, which is primarily methane, for industrial and residential use, and wood for heating homes. Other less known examples are crop burning for agricultural purposes, burning residual oil in ships, and coke in industrial facilities and refineries. As mentioned, these are all examples of hydrocarbon fuels. A hydrocarbon is some molecule comprised of both carbon and hydrogen. All of the above examples, except wood and biomass, are fossil fuels, derived from crude oil or natural gas extracted deep underground the earth. The term fossil is because these raw fuel sources underground are formed from organic matter from the distant past, millions of years ago, that has been degraded, broken down, and subjected to high pressures from the overlying earth above them over the passage of time to today. In this sense, they are fossil-based. So how do air pollution emissions form from combustion? The next two slides will cover this. This slide shows the basic chemistry of combustion with reactants and products. The one on top shows a basic schematic, while the one on the bottom is more detailed. Looking at the top, the basic idea is that air and fuel, when subjected to sufficiently high temperatures, around a few thousand degrees Fahrenheit or more, chemically reacts and as a result releases heat energy and several other chemical compounds as products. The energy released from combustion sustains the high temperatures required to maintain combustion, provided a steady supply of fuel exists. Air pollution is among the list of products of the basic chemical reaction of combustion. Spanning this list, we see carbon dioxide, water vapor, and several of the species that we have identified in this class as common air pollutants. Finally, some of the air that was not consumed in the combustion process passes out in the exhaust. The bottom, more detailed depiction of the chemical reaction makes this more clear. We indicate a hydrocarbon fuel as CmHn, where M and N can be any number unique to the particular hydrocarbon fuel. For example, if M equals 1 and N equals 4, we have C1H4, or CH4, which is methane. We then denote air by its two main components, nitrogen and oxygen. We then denote the products of combustion into two classes. The main products are carbon dioxide and water vapor. These comprise the main products that are created from the carbon, hydrogen, and much of the oxygen in the original hydrocarbon fuel molecules and air. However, due to the variability and particular characteristics of the combustion process at any given instance or situation, other products can be formed in lesser amounts. These include our common air pollutants, carbon monoxide, sulfur dioxide, nitrogen oxides, particulates or smoke particles, and unburned hydrocarbons. Also, a portion of the air that is not fully consumed in the combustion process is passed out as N2 and O2. This slide provides further explanation. We saw in the previous slide that combustion of hydrocarbon fuel results in various chemical products of reaction, which depend on the characteristics of the combustion process. We can distinguish situations further by looking at complete versus incomplete combustion. Complete combustion is a theoretical condition in which all of the carbon in the hydrocarbon fuel is converted to CO2 and all of the hydrogen in the fuel to water vapor. As a result, Since all of the carbon is in CO2, no other carbon byproducts would be produced. Specifically, there would be no carbon monoxide, no smoke, and no unburned hydrocarbons. For most fuels, complete combustion requires a ratio of 14.7. Let's go back. For most fuels, complete combustion requires a ratio for the mass of air to the mass of fuel equal to around 14.7. That is, by mass, there is 14.7 more air than fuel in the combustion chamber. This is called the stoichiometric ratio. Incomplete combustion is when combustion takes place in conditions other than stoichiometric, which is generally the case since it is almost impossible in practice to maintain the stoichiometric ratio at all times during combustion. Fuel-rich conditions are those when the ratio is less than 14.7, and therefore there is more fuel relative to air than that required for stoichiometric combustion. Fuel-lean conditions are those when the ratio is greater than 14.7, and therefore there is more air relative to fuel than required for stoichiometric combustion. In fuel-rich combustion, there is more excess air. No, sorry, take that back. In fuel-rich conditions, since there is excess fuel, there tends to be other carbon products besides CO2 produced, specifically carbon monoxide, smoke, and unburned hydrocarbons. In fuel-lean conditions, there is more excess air and generally higher combustion temperatures, which tends to favor higher NOx production and little, if any, CO, smoke, and unburned hydrocarbons. Finally, any sulfur in the fuel will generally be reacted to sulfur dioxide, regardless of air-fuel conditions. Coal is the hydrocarbon fuel most associated with high sulfur content, and therefore most associated with SO2 emissions, as we have said in previous lectures. Some diesel fuels also contain high sulfur, and in fact, California has regulations to require low sulfur diesel fuels in trucks registered in the state. From these points, we can look at a very basic general comparison between the composition of clean air versus the composition of exhaust combustion gas, directly exiting a combustion source. Clean air is mainly comprised of nitrogen, oxygen, and water vapor. We also indicate the small percentage of carbon dioxide, 0.04% or 400 ppm. Exhaust combustion gas, on the other hand, has a different breakdown. We present here a typical breakdown. The main thing to note is the reduction of oxygen levels completely to zero if combustion is complete and all oxygen is consumed, and an increase in carbon dioxide, which is the main product of the combustion reaction burning the carbon-based fuel. Water vapor percentages also rise, since water vapor is a natural product of combustion as well. Finally, we note the trace percentages of various byproducts of combustion associated with air pollution: carbon monoxide, sulfur dioxide, NOx, particulates, and unburned hydrocarbon gases, among others. Again, this is a very basic breakdown. A specific breakdown depends very much on the specifics of the combustion process, fuel burned, and other factors. Much air pollution regulatory effort is aimed at developing technologies that manage the combustion process and conditions in ways that minimize the amount of these trace air pollutant gases and species emitted. We now turn to other emission processes, which we will cover in less detail. One of these is fugitive emissions. These collectively comprise any process by which pollutants get emitted to the atmosphere as a result of escapes through equipment. These could be leaky valves, vents, pipes, or any other of a multitude of equipment within facilities. Fugitive emissions generally refer to gases, However, fugitive dust particulate can also result. For example, escapes of particulate matter during excavation, mining, or construction. Shown on this slide are some photographs of common fugitive emission sources. Oil extraction, indicated by the left photo, is a common source of fugitive gas emissions, and much recent attention due to air pollution concerns is paid to communities living near oil extraction facilities. There is also considerable attention paid to fugitive methane releases from oil extraction facilities for climate change concerns, since methane is a strong greenhouse gas. The photos on the right depict some common ways fugitive emissions occur due to the flow of materials through industrial facilities. Evaporative emissions are similar to fugitive emissions, but particularly centered on vaporization of liquid hydrocarbon and other compounds exposed to air. Another more technical term for evaporation is volatilization. A class of air pollutant species called volatile organic compounds are a subset of hydrocarbon compounds especially prone to release to the atmosphere through evaporative emissions. Any industrial facility dealing with liquefied chemicals, generally hydrocarbon, are possible sources of evaporative emissions in VOCs. The most readily identifiable example for students in this course may be a gas station, where filling of fuel results in some of the gasoline evaporating into the air. We can smell this, the familiar sweet, oily smell of gasoline. Other examples familiar to students are paints and household chemicals. This slide presents further details on VOCs, or volatile organic compounds. We particularly note the BTEX compound, benzene, toluene, ethene, and xylene, which are carcinogens. VOCs, as we will learn, also play an important role in the formation of photochemical smog. This will be covered in the next course module. Windblown dust and fugitive dust is another important air pollution emission process. The photographs show examples of this. The dust kicked up during construction activity in the upper left photograph, or by strong winds in the other photographs. Fugitive dust poses health risks. If inhaled, it can cause breathing difficulties. Also, a fungus living in the soil called coccidiodimycosis, if inhaled, can cause a very serious long-term sickness called valley fever, which is growing in incidence in recent years in the southwestern United States and California. Inhalation of fugitive and windblown dust is thought to be among the main causes of valley fever. As seen by the bullets for windblown dust, generally strong winds is required for this to happen, greater than 10 miles per hour sustained. Finally, we note wildfires, which are becoming more and more serious and frequent as climate warming proceeds. This is a major natural combustion source, which produces many pollutants, the most important of which being smoke. Being such large events that consume much biomass, the effects of wildfire smoke span large areas and affect many people. PM10 and PM2.5 concentrations during major wildfire events are generally many times higher than ambient air standards for PM10 and PM2.5. The photograph on the left shows the black smoke associated with wildfires, and the photograph on the right is taken from space of the major Campfire wildfire episode of November 2018, which affected a wide area of Northern California for a couple of weeks.